Hey nerds, time for another Q&A session. Now, this month we've been talking all about could we build artificial gravity? And very excitingly, it turns out, yeah, we kind of can. So it is legitimately just an engineering problem. And it's always exciting when we get to say that instead of, hey, we're breaking the laws of physics. But of course, that led to a bunch of questions. Now, if you don't know me, my name is Abby. I am a physicist. I'm just finishing up my PhD in physics at the University of Oxford. And I like to talk about the science of science fiction. I like to do this because I just think it's a fun, this isn't about breaking down sci-fi or criticizing it or anything. It's because I love it. So this is about actually just celebrating the way that they use science and then seeing what we can learn about the real world or what's really possible with what we currently know and understand about physics. And it's also a good way to try to break down some really complicated topics. When I do a video, so I do them once a month, we get one main video every month. And then I realized last month when I did the warp video, there were so many questions that I thought, hey, maybe I should just do like a Q&A video. And I trialed it last month. You guys seemed to kind of enjoy it. And I actually just enjoyed it. It's a good opportunity for me to be able to answer some of the questions that just come up a lot when we talk about some of these topics. So I'm just going to keep doing it. These are not they're not in the exact same style as my monthly videos. I'm trying to do them just a little bit more free. So I hope that you follow along with it. And yeah, let's get into it. Okay, so first question. Could a spaceship fly in a helical path to create artificial gravity? I love this question because intuitively, it sounds like it would make sense, right? You just think, well, yeah, you just need like a curved path, so why not a helical path? Now, sorry, if you don't know what we mean by helical, think of a corkscrew, okay? So just going you're moving in a circle or on a curved path, but you're also moving forward with each stage. So it's not like a perfect circle, it's that twisty, spirally curve. Now, this is obviously in relation to the part in the video where we talked about centrifuges. So a centrifuge works, or a centrifuge creates this artificial gravity, the pseudo force, because it's forcing you to move in a circle, okay? Your body wants to go straight. The floor, though, keeps turning underneath you. And the inward force that you're constantly resisting feels like gravity. So that I understand why that would lead people to think, well, a helix is also curved, so couldn't we just follow this corkscrew path through space and get the same effect? Now, the problem here, okay, so centrifuges work because the curvature is constant. Your path is a perfect circle in a flat plane. The direction of that inward acceleration that you're getting, which is the centripetal acceleration, is always the same. Your down is always towards the center, and the floor is always pushing you in that direction. Now, the key here is the force vectors, okay? You have the constant direction and the constant magnitude if you keep your speed constant. That's why they experience, or that's why what you experience in that system feels like gravity. Circle is, smooth, predictable, and it's stable. Helix is not a circle. The curvature vector keeps rotating in 3 dimensions, okay? So a helix is a spiral in 3D. Part of your motion curves horizontally, part of it will curve vertically. The curvature vector is constantly changing direction. That means that the required centripetal acceleration that's pulling you in is also changing direction. So the gravity that you'd feel would never point in just one way. It wouldn't be steady and it wouldn't align with the floor the way that it does in the circle configuration. So you would constantly be feeling this shifting tilt. The floor wouldn't feel like the down direction and your inner ear would lose its mind. Coriolis is gonna go crazy. But something that's really interesting here is about the difference between rotating the ship versus curving its path. Because the helical configuration would be curving the ship's path through space, whereas the centrifuge is actually rotating around the center point of the ship, right? Or the center of mass of the ship. So centrifuges produce artificial gravity because you are rotating relative to the ship. In a helical trajectory, the ship would be curving relative to space, but the interior frame isn't rotating with respect to you. You and the ship would still be in free fall together. You see, artificial gravity depends on the reference frame. Now, if you're not accelerating relative to the ship's interior, you're not going to feel anything. This is why astronauts in orbit float, because they're in a perfectly curved path around the Earth. They've got really high speed, they've got a constant curvature, but they're still weightless. And that's because the ship and the astronaut follow the curve together. If orbital curvature can't give you gravity, then a helix isn't going to give you gravity either. What you need is the difference between the circular orbit around the center of mass. So I think it's a really fun idea, and I think there's probably a really clever way maybe that someone could come up with it from like a science fiction point of view, but it's not going to work like physically for us. Okay, question number 2. Should thrust gravity be uniform along a ship, and what is Born rigidity? Okay, so this comes from the part where I talked about the equivalence principle. And from that, I made a comment about how if you have a long enough ship, the acceleration will be different at the nose versus the base. And it made a lot of people upset because, as a lot of people pointed out, acceleration should be uniform. But this is where Born rigidity comes into it. So let me explain. If your spaceship accelerates at 1g, the crew will feel 1g all the way down its length, right? That's the equivalence principle, basically. But relativity, and it's always relativity, you guys, kind of ruins the simplicity if the ship is long enough. So the equivalence principle says that if you're in a sealed room, standing on Earth under gravity or accelerating upward at 1g in deep space, you can't tell the difference locally. Locally is the key word here, right? Because it means that in a small region, like in a room on Earth or in a small part of a ship in space, inside that space, gravity and acceleration are indistinguishable from the perspective of your body, right? The feel and the effects on your body are all exactly the same as they would be if you were standing on Earth. But the moment that you stretch that space out, relativity has some things to say. Now, in relativity, you cannot accelerate a long object as one perfectly rigid block. That's where Born rigidity comes into it, right? In Newtonian physics, you can imagine grabbing a spaceship by the engine and just shoving like the whole thing forward instantly, right? Everything accelerates together, no problem. But in relativity, information cannot travel faster than light, and at the same time is not a universal concept. So if you try to accelerate a long ship uniformly, so like the same acceleration everywhere, relativity says you're actually stretching the ship. You're trying to pull the nose before the information about the pull reaches the front. So a perfectly rigid body cannot exist in relativity. You have to accelerate different parts differently to keep the shape intact, and that's Born rigidity. So to preserve the ship's shape from its own perspective, it means no stretching and no compression. So the rear, which is closest to the engine, must accelerate slightly more than the front. The front must accelerate slightly less, because the rear has to catch up to the front in relativistic terms. Now, if they both accelerated at exactly the same proper acceleration, the rear would be trying to pull the front faster than the front is ready to move. So Born rigidity mathematically prescribes the exact gradient of acceleration that you need in order to keep the length of the ship constant. So what does that mean for artificial gravity? Well, it means that the back of the ship feels a slightly stronger gravity than the front. And there's like this tiny gravitational gradient that goes all the way along the ship. Now, on a normal spaceship, like 100 meters or something like that, the difference is microscopic. Like it's barely, there's no point in talking about it. You'll never notice it. You need like hundreds of meters, kilometer long ships in order for this to actually be a measurable effect. The point is that relativity says you can't avoid this gradient though. Now, this does not violate the equivalence principle, because the equivalence principle says that gravity and acceleration are equivalent locally. Born rigidity tells you what happens when you go beyond the local frame. this is really similar to like tidal forces that exist in gravity, because gravity varies with distance from the source and acceleration varies with distance from the engine if you want to keep the ship rigid. So thrust gravity is almost uniform, but if your ship is long enough, then relativity forces a small but very real gradient. Okay, question number 3 is more of a comment that came up quite a lot. So something people get very upset about, like people get quite emotional, aggressive about this, is when we refer to gravity as a force. A lot of people are really, really bothered by this. So let's talk about it. Is gravity a force or not? Is it still, can we refer to it as a fundamental force? Is that the right language to use? So the problem is when we're talking about like everyday physics language, whether we're talking about Newtonian physics, whether we're talking about Einsteinian physics, whether we're talking about particle physics models, all of these different ideas use the word force in slightly different ways. So Newton's gravity is a force. There is no getting around that, right? In Newton's picture, you have two masses that pull on each other instantly across a distance. It is a very simple model that we have been able to use and still continue to use, and it was accurate enough to allow us to be able to land on the moon, to send probes across the solar system, to explain tides, to keep satellites in orbit. For all of that, in that framework, we don't need general relativity. We can just use Newton's force of gravity. And so in that context, when we're talking about Newtonian gravity, force is absolutely the correct term to use. That's how it's described mathematically in his equations. And that is the first thing that we learn when we learn about gravity. Now, some people want it to be taught the other way around. I don't know if that's intuitively right to maybe teach Einsteinian physics before teaching Newtonian physics. I don't know. We tend to like build on knowledge, right? So it's important to start with a simple model and build on it. That's what we always do in physics. Now, so when we talk about just everyday concepts of gravity related to Newton mathematically and the discussion around it, gravity as a force. But then when we talk about Einstein, we don't talk about it in that way. So in Einstein's picture, gravity is not a pull. It is the curvature of space-time. Masses distort space-time. Objects follow the straightest possible path through that curvature. These straight paths are called geodesics. And in that model, planets orbit not because they're pulled, but because they're following these geodesics. And weight is the floor pushing up on you, not gravity pulling you down. So gravity is not a force in this description, it's geometry. But they're both correct views. You see, Newton's force picture is an approximation of Einstein's curved space-time, and it's valid when speeds are small compared to light, when gravitational fields are weak, and when precision requirements are like not really, you don't need to be that precise, basically. That covers basically everything that a normal human ever deals with. Einstein's picture comes into it when we need to talk about how you orbit black holes, or you do GPS corrections, or you study gravitational waves, or if you want to go near to light speed, you design fantasy level spacecraft. Then in that case, gravity is a force in Newton's domain and gravity is not a force in Einstein's domain, but both of them can be thought of as correct and useful. Now, in terms of it being a fundamental force, which is what I referred to, I think this was when we were talking about gravitons, where I probably said something like that gravity is one of the 4 fundamental forces. So in that sense, in terms of standard model physics, the standard model of particle physics, it's there are 4 fundamental interactions. So I don't know, maybe in that sense I should say interaction instead of force, probably, and I should probably correct myself to do that in future, because the interactions that we're talking about are the strong interaction, the weak interaction, electromagnetic interaction, and gravitational interaction. But we do also refer to them as forces, right? It's the strong force, the weak force, the electromagnetic force, and then the gravitational force. So this comes from particle physics and cosmology, and this is where we treat gravity as a fundamental interaction, even though its mathematical form looks totally different from the others. So Einstein's geometry doesn't contradict calling it a fundamental interaction. It just means that it doesn't behave like a field force the way electromagnetism does. And we don't know yet what the full description of gravity would be in terms of the standard model, because we don't know what a quantum description of gravity is. We haven't developed that yet. We may never develop it. So I think people just get really mad about the wording. They kind of really feel like saying gravity as a force is wrong. But like physicists will happily say gravitational force, force of gravity, gravity is a fundamental force, because the terminology depends on the model that you're using at that moment. It's about context, not contradiction. So like Einstein describing gravity as the curvature of space-time is more mathematically correct, but that doesn't erase what Newton did, and it doesn't erase the discussions in standard model. These are all like extensions. It's all different ways to mathematically discuss the same concept, but at different scales, right? So we've got Newton being classical, we've got Einstein being general relativity, so being like large scale, and then you have quantum being teeny tiny scale. And they all might need things to be discussed and described in different ways. But we're not going to use Einstein's general relativity when we're talking about like a ball falling off a ledge. It's not necessary to do that. So gravity is a force in Newton's world, it's geometry in Einstein's world, and it's fundamental interaction in modern physics. So there's no conflict between the three of them, let's be clear. Now people can disagree with that, and people might feel like, oh no, it's the Einstein's is the be all and end all. But again, it just depends on the context of what you want to discuss at the time as to how you're going to talk about it. And it's not really that it's incorrect to say that gravity is a force, it just means that, you know, you wouldn't say it if you're talking about general relativity, but you will if you're talking about Newton. And that's it. All right, question number 4. Is inertia the same thing as gravity? Now, this came up a few times. People kept kind of making comments about how they wished sci-fi would talk about the moment of inertia more. And I honestly was a bit confused as to what some of the comments were trying to get at, or what their gripe was about what we should be talking about. So some of them were very clearly related to conspiracy theories. So I just thought, let's just discuss what the difference between inertia and gravity is, and maybe that might help some people understand a bit more. Okay, so the comments ranged from saying that like gravity is fake and inertia is real, to gravity is just inertia in disguise, to UFOs cancel inertia and they don't feel gravity, or stuff like that. And I think what it is it's coming from misunderstandings of the equivalence principle. So basically, Einstein and gravity feel the same. Einstein and gravity, what? Inertia and gravity feel the same in terms of the equivalence principle. So when you're standing on Earth, that's gravity. When you're inside a rocket accelerating at 9.81 meters per second squared, that is because of inertia. But the force that you feel pushing you into the floor is indistinguishable physically. Like, so I've said that before. The way that your body feels and responds to that force that it is feeling is the same whether you're standing on Earth or whether you're inside the rocket. Your body can't tell the difference between what you're experiencing locally. That's the equivalence principle, but the actual physics of what's happening in each scenario rises differently. So on Earth, it's gravity, mass energy, curving space-time, tells objects what paths to follow. It's not a resistance, it's the shape of space itself. Whereas inertia is an intrinsic property of mass, okay? So an object resists change to its motion. That's how an object gets mass, depends on how much it interacts with the Higgs field. And how much the object interacts with the Higgs field determines how much it resists changes to its motion, and then that gets quantified as mass. It has nothing to do with space-time curvature. It comes from just the structure of matter. So that's the Higgs field. There's also like some QCD binding in there, but quantum chromodynamics, but we're not going to get into that. We ain't got time for that. I don't know why people would think inertia is the real one. But the thing as well is, the most important point here is they're not interchangeable, right? Gravity and inertia are not like, you don't just switch them around. If you got rid of gravity but kept inertia, planets would like fly off into space, right? You wouldn't have orbits anymore. You wouldn't have tides. The universe would make no sense. But if you killed inertia but kept gravity, then anything with mass would like collapse under its own attraction. Atoms would break, chemistry would fail, no universe. But very, very different consequences, right? Very, very different things happening. So yeah, when we talk about the equivalence principle, they are two different things that provide the exact same sensation, which is why we talk about thrust being an artificial gravity, because it helps your body to respond and react in the way that you would need it to if you wanted to have long-term space travel. So they feel identical in that respect locally, but they're not the same thing. They're completely different pieces of the universe and completely different like physics. Why would I say pieces of the universe? That's a weird thing to say. Different physics, you guys. I told you this would be a little bit rambly and chaotic. Wait, I didn't tell you that yet. This is going to be a bit rambly and chaotic. Moving on. Question number 5. Could diamagnetism be used to create artificial gravity? This came up a lot. A lot of comments and discussion around magnetism in general being used. Now, I already kind of answered this in the main video because I talked about magnetic boots, and I talked about how like a magnet doesn't actually have the same pull on your body. Like, you know, having something that connects you or drags on you in such a way that pulls you down in the way that like magnetic boots would, doesn't mean that physically, like internally in your body, that it's having a response to the magnet. It's not. It's just the connection of the materials. That's where the response is. But in diamagnetism, people like to talk about the frog experiment. So let's start with what diamagnetism is, right? So it's, okay, all materials are made of atoms, right? We know this. We have electrons orbiting nuclei. Now, when you apply a magnetic field to certain materials, the electrons will slightly adjust their motion. This produces an induced magnetic moment opposite to the applied field. So the opposite kind of leads to repulsion, and that effect is diamagnetism. So diamagnetic materials are weakly repelled by magnetic fields, and humans, because we are mostly water, are diamagnetic. This is where we get into the conspiracy stuff. You guys stay with me. Let's not go there. Oh my God. I've only just realized that that's where all the conspiracy stuff about magnetic. Oh God. Someday I'm going to have to talk about what all that like healing stuff is with like frequencies and fields and the way people talk about the connection to the earth. I don't know. Anywho, why does the levitating frog work? Now, the reason the frog floats in the levitating frog is because it's being pushed upwards by a magnetic force that is counteracting gravity, okay? To cancel gravity, the 1g downward, you need a magnetic force that is equal and opposite to 1g. That requires about 16 Tesla for the frog, with extremely steep gradients. And the reason that this is important is that the frog only floats because we overpower gravity with magnetic repulsion. We are not creating gravity, we're nullifying it. And the distinction does matter here. So diamagnetism always pushes things towards regions of weaker magnetic field. So materials are pushed into regions of smaller magnetic fields, and that means that diamagnetism pushes you away from strong magnetic fields. You can't flip that, right? So there's no magnetic like south gravity, which will kill any magnetic gravity plating ideas. But now I'm thinking like, why wouldn't just put the magnet on the ceiling, right? So it pushes you downward. But if you put a strong magnetic field on the ceiling, then you get repulsion away from the ceiling, but not a pull towards the floor. That's the point, right? That's the point. It's the pull that you need. The importance for the body is the pull that it feels towards the floor. It's the loading that your body physically gets. So because the diamagnetic field is pushing you away rather than pulling you towards, it doesn't work, like it doesn't have the same physical effect to be able to create gravity. Okay, next question. This is a great question, right? So does storing data have mass, and could extreme data density create gravity? This is about information theory, and then we're going to add some relativity to it. So storing data changes the mass of a device, right? And here's the physics, okay? Changing a bit from 0 to 1, or like from 1 to 0, stores or releases energy. So energy has mass thanks to E equals mc squared. Therefore, a full SSD does weigh more than an empty one. This isn't like speculation or anything, it's just how the math works. So my SSD card, after I record this video, is going to be heavier than it was when I first put it in to start. But the amount of mass, you guys, it's so small. It's so tiny. Like the energy charge per bit is roughly 10 to the minus 21 joules, which means that the mass change is about 10 to the minus 38 kilograms per bit. Okay, think about it this way. A gigabyte is 8 billion bits. So 8 billion bits times that mass change means that just a normal, like an 8 gig hard drive would gain 10 to the minus 29 kilograms. It's not even worth talking about. Like it's not even, I don't even know how to give you that in the context of anything around us that weighs anything, because I have no context. The energy equivalent that you have in the data in a hard drive, you would still need that equivalence of the Earth. You know, so you'd need enough hard drives that were the size of the Earth, basically, or had made up the energy that the mass of the Earth has in order for it to actually create gravity. So it doesn't cheat the system in any way. It doesn't actually give you anything extra. I think it's an interesting concept, because we kind of think of like data or this as being like this abstract like nothingness. So it's like you're kind of getting weight or getting like this effect from nothing, but it's not nothing. It's the actual processes that are happening inside the system is happening through interactions and through energy, which in turn can add mass, which we'll read as a heavier weight for us. So yeah, so that's kind of it. It's a super fun idea, and I do love that kind of fun fact anyway, that like storing data adds mass. But it's so little that it's effectively zero, but it also doesn't mean that you need less. You still need the same amount of energy that you would need for the planet Earth. Let's move on to the last question, because I think that this is probably the question that came up the most, and I get why, and it makes sense. So we're back to the centrifuges, and the question that kept coming up was, if you jump inside a rotating centrifuge, do you float? Because we're talking about the forces that you feel, right? We're talking about that centripetal acceleration pulling you in, and the centrifugal force pushing you towards the edge, and the curved path, meaning that the floor is always beneath you as you move around. So, you know, depending on the size, you have to kind of counter like some Coriolis effects for sure, but like we've learned that astronauts are fairly adaptable, and they can actually figure that out pretty quickly, so long as it's not insane rotations. But that's the big question, is if it requires that those forces and that pushes that are pulling you while your feet are on the floor, if you actually just jump up, are you suddenly outside of that centrifuge's frame, and are you just going to float there? So on the floor, the gravity that you feel is centrifugal. Your body wants to move straight. The floor keeps forcing you to move in a circle. That's what's happening. You're being like sent off that way, but the floor is curving around. So as you're going that way, the floor is moving. So the floor is always underneath you as you're doing that. So the inward force that you feel as down is just the floor pushing back on you. And that feels exactly, or some, as close to gravity as we can get. When you jump, you leave that rotating frame. The moment your feet leave the floor, they're no longer being pushed into the circular motion. So you stop rotating with the habitat and you begin traveling in a straight line in inertial space. But the room around you keeps rotating. So you are moving in a straight line, slightly drifting upwards, but the floor is curved and moving around you. So you're eventually going to meet the floor again. You're on a straight path. This is on a curved path. You will eventually meet the floor again. You just won't land in the same place that you jumped from. Now, the effect is going to depend on how big the ring is. So if it's a smaller ring, if it's like a small radius, then it's going to feel like the effect's going to be a lot stronger. But if you have like a much larger radius, then the drifts will be pretty small and you kind of basically jump normally. There'll be some like Coriolis effects in terms of like how your inner ear is registering, like how your body is moving, but how it's registering the motion outside of it is going to have some different things. But the really interesting part, because somebody did bring this up as well, is what about the air? And this is the thing about the centrifuges, right? Is the air is also rotating. So you have atmosphere inside your centrifuge. And so the air is being dragged along by friction. It's rotating with the station. So when you jump, you're then moving through rotating air. And the air resistance will gradually force you back into the rotating frame. So you will get like nudged back into sync a little bit as well before you land. So there's a lot of different things happening. But yeah, I guess you would like effectively sort of drift. You wouldn't float in like the same spot. You wouldn't just like be up and then it's moving around and you're just like hovering there. You'll jump. It will, the frame will still rotate, but you will slightly drift so that you will eventually end up on the floor again, is the kind of the crux of it. But yeah, that was a really interesting one to try to look into and be looking at like what the actual effects are and what would happen. And that's all I have. I do feel like this was maybe a little bit more chaotic than the last one, so I do apologize if it come across. Maybe that's just how I feel in the recording. Hopefully the edit will be better. But yeah, I hope that you guys enjoyed that, or I hope that answered some of the questions that you had. And like I said, this is a work in progress. The Q&A videos, we'll see how they progress. We'll see if I get better. We'll see if, I change ever so slightly how I do it, depending on what you guys want or how you are feeling about it. I'm open to your thoughts and suggestions. My channel is about me getting to talk about the stuff that I really want to talk about, but it's also about me being able to answer questions that I see come up a lot if I think I have an answer for them. But it's also about you guys. You're here, you support me, you're enjoying what I'm doing. So it's important to me that I'm getting to talk about the stuff that I like, that you also like, I want us to be, it's a team effort. So yeah. Oh, sorry, notes. Okay. I did this last time as well, and I should do this. Videos are the beginning of the month, every month. I'm going to slightly change. Well, I used to do it so it was like every 4 weeks, but it feels really scatty. So I'm thinking about changing it and doing it like either the first of the month, every month, or doing the first Sunday of the month. Let me know which one you think would work best. Second thing is that then 2 weeks after that is always the Patreon/YouTube memberships video. So that came out last week for the artificial gravity topic, and I talked about interstellar and Miller's planet. It's been on my mind for a very long time. I've done a lot of videos about the science of interstellar before, but I've never really talked about the gravity effects on Miller's planet. So I really wanted to talk about that. Like, how does the time dilation get created on Miller's planet? How does the planet even exist in the orbit that it exists in? Most of what I talk about in that video is just what Kip Thorne has said, but I stand by anything he says about what he did for the science of that movie. So I stand by it 100%. So if you're interested, you can join Patreon or YouTube memberships. If you're not interested, that's fine. Don't worry about it. But we still have plenty of other stuff for us. Speaking of, next week is the new episode, which, no surprises here, you guys picked teleportation. Of course you did. I knew you were going to. But can I tell you, when I put the polls up, right, for the first maybe the first 5 hours or something, it was other topics. And I was like, what's going on, you guys? I thought you were going to pick teleportation. I was really ready to talk about teleportation. I was so sure you were going to pick it. And then, yeah, you guys, within a day, it was clear. You didn't do me dirty. Thank you for that. So, next week, teleportation. It's going to be a big one. It's a lot to cover, a lot of quantum to cover as well. So, hope you guys are ready for it. Thank you for hanging out with me and following along with what I am doing. I appreciate it. And especially those of you who do watch these Q&A videos, because I just think it's a nice time where I get to break down the stuff that you guys have been asking me in the comments. And yeah, okay. I'm going to stop talking now. Bye.
That may be impossible, sir.
Things are only impossible until they're not.
Yes, sir.